Hello, welcome everyone. Feel free to say hi if you haven't already. It's great to see some people already here. I hope we're doing well. I'm just going to check everyone can hear me, but do say hi in the chat if you haven't already. Welcome. Some of you, I think, were at the GCSE session as well, so it's lovely to see you back. And obviously, we're going to be looking at an A-level topic today. So this is quite a kind of big, challenging idea in the A-level that comes up in the pure part of the course. The ideas come up in the pure part of the course of binomials, but this is very much a part of the statistics side of it. So we're looking at the binomial distribution. So binomial expansion comes up in pure, and we're going to recap that, but we are also going to be looking predominantly today at binomial distribution, and that is a statistics topic. So all good, thanks. Thank you for the comments, and great to see so many people joining already. I'm about to share the screen. I'll just give everyone a chance to say hello, and do let me know if you've done this topic before. So if you've done the binomial distribution as part of the statistics in your A-level, it is often covered in year 12. So this is an idea that's, depending on your course, might be done in year 12, but it's very much the statistics side of the course. So let me know if you've done this before. For those of you, this might be revision. For some people, this might be quite new. But we're going to be looking at the binomial distribution. Welcome. I'm going to just share my screen now, and hopefully we'll be able to see this. So binomial distribution is something we're going to look at. Let's have a little look. So hopefully we can all see this. I'm just going to share it so it's full screen. I'll talk a little bit about Snap Revise as well and upcoming web classes for those that are interested in the other topics we do. This is just an example of a web class on a specific statistics topic that will be covered by all exam boards. So hopefully useful to everyone doing their A-levels. Oh, okay, that's interesting to hear. So obviously some schools and colleges sort of divide the A-level up differently. So this will be a good one to look at. Welcome to everyone joining, and thank you so much for saying hello and everything already. And lovely to hear that some people have done this topic and get a sense of, for some people this is new, but for others it's revision. So thanks for letting me know. And do obviously feel free to ask questions and share answers as we go. So we're going to be looking at the binomial distribution today. And I'm going to get this started because I think, why not? I don't want to waste any time. We'll get cracking. So I'm Max, I'm head of maths at Snap Revise. I did a maths degree and I've been teaching pretty much ever since, and I teach A-level for the last sort of 4 years or so. So I've seen the changes in the A-level as well, and the exams have been rejigged and kind of repackaged, but the content is largely the same. So today we've got this code for a week's free trial of web classes and the resources on the Snap Revise platform. So I'll talk a little bit more about that at the end, but do make a note if you're interested, and if you find this useful, it might be something worth looking at. We run a lot of web classes and drop-in sessions where you can ask about specific topics you might be struggling with at school or you want to get ahead with. You might have a test on stuff. So I'll talk about that towards the end, but there is a code for the checkout. So please stay for the session, see how you find it, and I'll talk about where to use that at the end of the session. Okay, cool. So as I said, please do feel free to write in the chat any questions and answers as we go. I'm going to carry on. What we're going to look at today is we're going to look at binomial expansions and how they can be used to calculate probabilities, determine what situations binomial distributions can be applied to, and calculate probabilities using the binomial distribution. So this is a topic that does grow into hypothesis testing and some bigger scenarios, but effectively it starts really from ideas we've seen at GCSE of things like tree diagrams and multiplying across different scenarios within the realms of probability. So it's very much a probability topic as part of the statistics side of the A-level. So what we're going to do, we'll have a little look at this topic today. The things we should already know from the A-level. So before you cover this in stats, you should have covered in pure this idea of binomial expansion. So this notation, we should hopefully recognize that this means n choose r. So who has seen that before? And on your calculator, the way you get that choose idea up is if you go shift and then the divide button, it puts like the letter C, and you can put the numbers either side of that to give you the combinations of choosing. So the formula for this is n factorial over r factorial n minus r factorial. So it would be good to see who's seen this before. Welcome if you're just joining. That's lovely. Thanks for letting me know, guys. That's brilliant. So this is part of the pure side of the course. So you may well have seen that. And just a reminder of what a factorial is n factorial is basically 1 times 2 times 3 times 4, all the way up to whatever n is, times all the numbers down to 1. And so you've hopefully seen that within pure, where you're doing like binomial expansions. So something like this, you do a to the n, x to the n, and then it'd be n, a to the n minus 1, x to the, sorry, that would be a to the 1, x to the n. No, I'm getting it confused here. And so on. So basically what you end up with is n choose r, a to the r, x to the r, b to the n minus r. And you might have learned it in slightly different ways, depending on how you've seen it in a formula book or how it is in your textbook. But basically, you should have seen this within the realms of binomial expansion, and you would have likely covered Pascal's triangle. Yes, yeah, well done, good question. So this is when you're multiplying out lots of brackets, the power of one increases, the other decreases, and the n choose r bit is the number of ways of combinations of those multiplications you could have. And so this is basically tying into the statistics side of it, because effectively what we're looking at with the binomial distribution is if you had a massive tree diagram and you had to multiply over loads of branches, you don't want to draw that out. You want to basically say, how many different ways could this happen? And that's the n choose r part. And then you're going to say, this is the probability of success, this is the probability of failure, times it all together. And that's how this relates, because there's two scenarios going on. Just like in a bracket, there's an x bit maybe in a constant part, and you're timesing them together. This is like the probability of it happening, the probability of it not happening, and timesing it together. So this is how it relates to the bit you've seen with pure. And that is the topic with Pascal's triangle. So well done, brilliant comments. So probabilities, things we should know about probabilities. So some kind of keywords and ideas. We've hopefully seen this before. The idea of a sample space is basically a set of all outcomes. So it is the set of all possible outcomes, all outcomes. And what we've got is, for example, sometimes A is a group of outcomes. A is a set or an event. And then what we might use, so if I use the letter A, I'm just using as an example, then what we have is we have this notation, P of A is basically the probability of A successfully happening. So probability A happens. And then this one, probability of not A, is basically 1 minus the probability of A. So that A prime, that A dash means not A, and that's called the complement of A. And then you may have also seen within statistics, those that have done it before, and I appreciate that some people haven't touched this part of the course yet, you haven't seen this. We look at independent events where the probability of the intersection is the probability of the two things times together. Now, you have actually seen this idea at GCSE. Independent events are basically like when you're timesing across branches on a tree diagram. This thing happens, then this thing happens, so you times the probabilities together. So if each go or scenario is independent of the other, it means you can times the probabilities. So it's not a new idea, it's something we've seen before at GCSE, it's just the notation is obviously getting slightly more involved at A level. And the other types of events we look at and pay particular attention to at A level are these ones called mutually exclusive, which basically means they can't happen at the same time. So the probability that both or either or happen, the union, is the two probabilities added up. Cool. So I'm going to move on and look specifically at the binomial distribution today. And this is, as I said, regardless of what exam board you're using, this is definitely on the A level. So binomial distribution is really important to the statistics part of the course. So we're going to look at the binomial distribution now and what it actually is. And I'm going to break it down in terms of the different probabilities involved. So if you were imagining this massive expansion of p plus 1 minus p to the power of n, that looks horrible, but say p is just a number like 0.2, 1 minus p is 0.8, and you're doing that to a power, then you would do much like you'd do in this binomial scenario here. So hopefully that sort of setup is familiar. Now, the reason we've used p and 1 minus p is we can think of p as the probability something happens and 1 minus the probability that it doesn't happen. So 1 minus p is basically the probability, and this will hopefully make sense in a minute why I'm showing you this sort of breakdown, the probability of the event not occurring. Does that make sense to everyone? So if p is the probability it does happen, 1 minus p is the probability that it doesn't happen. So the probability of the event not occurring. Does that sort of make sense? And then I'll break this down and put it in context, and we'll look at some calculations. So is that sort of clear? So that's the probability of the event not occurring, 1 minus p. Lovely. So if I were to times the probability of it happening to some power by the probability of it not happening to the total number of goes minus that power, are we happy that that's basically like on a tree diagram, success, 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 like win, 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 times fail, 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 fail. So what you've basically done is across however many branches it is, say it was like 10 games, and I said, right, I win 6 times and I lose 4 times. I would do the probability of winning times the probability of winning to the power 6 times the probability of losing to the power of 4, because that's going across 10 branches like you would have seen at GCSE. So what this has basically done is I've done p times p times p, the probability of winning however many times multiplied by the chance of losing the rest of the times. So this is basically the probability of the thing occurring r times, where r is obviously just a number, and not occurring the rest of the times. Not occurring n minus r times. So hopefully that's clear that if I times all the probabilities that it happens by all the probabilities that it doesn't happen, that's like going across the branches of a tree diagram. So what this bit does is this is the number of combinations of how that could happen. So for example, if I have 10 goes, 10 games, and I win 6 of them, that means that I lose 4 of them. So I could do probability of a win times probability of a win times probability of win, so on, times 4 losses. And that's one specific route to how this could play out. But we know there's loads of different ways that you could win 6 times and lose 4 times, all different orders, all different combinations. So that's what this n choose r bit deals with. It deals with how many different ways of different routes you could take across maybe 10 branches for that scenario to play out. And effectively at the end, you have 6 wins and 4 losses. So that n choose r bit is really important because it tells you how many routes are there on your massive tree diagram. What are the probabilities times together? All the probabilities of success times all the probabilities of failure. And so what we've got here is this sort of little formula is how we calculate a binomial probability. And this is the probability. This is what we actually use, and we'll do it with some examples. Then I'm going to show you some really nice calculator shortcuts for this. So the probability of it occurring exactly r times in n trials. Right, the idea of this is to not draw a tick tree diagram because it would get overly confusing. But just to kind of contextualize what I'm saying is a binomial scenario where you have win and lose, say for example, win, lose, success or fail. As that carries on, the tree diagram gets a little bit crazy when there's loads of branches coming out of everywhere. So that would be, for example, for 2 goes. And so if, for example, we wanted multiple wins and multiple losses across a number of branches, you know that you would times them together across the branches, but there would be more than one way that that overall scenario could happen. So what I'm saying is if there were 10 goes, which would be ridiculous to draw as a tree, it would get too messy and it wouldn't fit on the page because they'd all have 2 branches coming out and it would just become a massive diagram. You know that there'll be so many wins and so many losing, and you times the probabilities together. But what this bit does is it tells you how many actual combinations you could have of that. So you could win, 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 lose, or win, lose, win, win. But ultimately the same effect happens. So that tells you how many ways and paths there are to that same ultimate outcome and adds them up. So what we're doing is we're looking at the probability of winning, probability of losing in the amounts we want, times by the number of ways that that can happen. And what we'll do is we'll see it with some examples now, but I'm really keen to get on to show you how to do this on a calculator and also put it in context of like some worded problems. So lovely, excellent. Thanks for the questions though, guys. This is brilliant. The other thing we need to know is the actual criteria for a binomial distribution, because they do ask this a lot. This is a really common exam question in statistics. So if we model a variable x, which might be the number of times I win a game or I get heads or tails on a coin or whatever it is, the way we know we're dealing with a binomial is the following 4 conditions. And they often ask you to sort of almost quote these or say why it's a binomial model. So one of them is that there are a fixed number of outcomes, a fixed number of trials. So for example, 10 goes. How many trials are there? So a fixed number of trials, n. And each trial has specifically 2 outcomes. So each trial, and now this definition, this set of 4 bullet points is really crucial. You know these and you can replicate this and explain this. So each trial only has 2 outcomes. Hence why it's binomial, 2 things, this one or this one, like the idea of binary or anything with 2 options. So each trial only has 2 outcomes for it to be this sort of distribution. And the easiest way to think of this is success or failure. The thing happens or it doesn't happen. It's one or the other. Otherwise, we'd have to use a different model. So this is for scenarios with win or lose, this or this. You can't have win, lose, draw. That wouldn't be a binomial. Okay. The next thing is that the probability of success each time has to be the same. So this is a really important condition. So it can't be that if I win once, I get more confident and I'm better chance of winning again. That wouldn't be this model either. So the probability of success is constant. We call it P, is constant. And then the 4th condition, and they hopefully are all fairly clear, is constant or is fixed. And then all trials are independent of each other. So they're not affecting the chance of the others. Okay, so all trials are independent. So please do ask any questions and let me know if you've seen this before. Because as I said, it's really common that this actually gets asked in the exams of each other. Let me check I'm writing the right thing. Yeah. So for example, if the question was, we might state that the random variable x, whatever the scenario is in a context, the random variable x is described by the binomial distribution And here's where we're going to see the quirky notation we need to learn. Described by the distribution. And so what we have is we have this cool little squiggly symbol. X follows the binomial distribution with n and p and whatever those values are. So this would be with n number of trials and p as the probability of success. And it will make more sense when we see it with some numbers. We do some examples as probability of success. Okay, so this notation here that we've got to become familiar with basically says that X follows the binomial distribution with whatever this number of is the number of goes, the number of trials, and P that's listed next to it is the probability on each go that you win. Okay, so this is the binomial distribution, and that's how you would state it for whatever random variable you're dealing with. So we will be looking at some exam questions, and I'm going to show you how to calculate it. And we're really going to get into these scenarios now. But could you let me know just quickly in the chat, a 1, 2, or a 3, how confident you're feeling with that sort of setup? So the idea of what a binomial is, the idea of binomial expansions, perhaps from pure, the kind of terminology with statistics that we may have seen before. Give me an idea, but no worries either way, because obviously this is, as I said, a big and quite specific A-level topic that's quite important to go through. So just give me an idea of if you find that straightforward so far, if it's kind of okay, you followed it, but it perhaps is quite new, or if it was quite confusing, do let me know as well. That's fine, but thank you for letting me know in the chat, guys, and do as we go, ask any questions. Brilliant. Right, I'm going to move that on. Do feel free to still tell me how you're feeling with it. And I'm going to show you some typical exam questions so we can see how this will come up. And then we'll start doing some calculations as well. What do we mean by the random variable X? So X might be something that's modeling the number of people winning a game of chess. And that's the random variable, the people playing the game of chess. So that's what we're modeling and what's the chance they win. So the random variable is basically the context or the scenario. Cool, the thing that is varying and changing that we're trying to work out. Great question. Right, so let's have a little look. Here is an example of a question here. Past experience has shown that when seeds of a certain type of plant, are planted, on average, 90% will germinate. A gardener plants 10 of these seeds in a tray and waits to see how many will germinate. Name an appropriate distribution with which to model the number of seeds, given the values of any parameters, and state any assumptions you need for it to be valid. So I'm just going to highlight some key bits of information here. 10 of these seeds, 90% will germinate. And you might think, well, okay, the only one I've done is the binomial distribution, so I'm guessing it's that. And you would be right, it is a binomial distribution, but we need to state why. So what we've got is we would say that X follows the binomial distribution where N is 10 and the probability of success is 0.9. So the actual random variable here, X, is the number of plants that successfully germinate. So the chance that that happens is 90% of the time. The number I'm planting is 10. And so this is a binomial. So this is kind of the answer to what we'd write for the binomial. They're the numbers. That's what we've got going on. It's a binomial distribution. Binomial distribution, the one we've been looking at. And as I said, the probability of success, the number of trials, N, equals 10. And so that's kind of what we've got. So X is not a value, X is a variable in this case. So we might be asked, well, what's the probability that out of these 10 goes, only 4 of them actually germinate? So X is a variable, it's not a specific value. We could be asked to work out the probability of a specific value happening. But this is the idea, is that it's actually a set of scenarios. So that's what we're looking at, but brilliant questions. So it's actually N and P that we have values for that are fixed. X is the variable. X is the thing that could change, and we're going to try and work out probabilities of. And the other thing it did actually say, because it was 4 marks, is state any assumptions needed for this model to be valid. So I'm saying it's a binomial model, but I've assumed some things by doing that. And if you go back to the 4 conditions we looked at over here, they've already told us some of this stuff. They've told us P and they've told us N. But what I'm going to say is the things we've had to assume in order to fit this to a binomial is that we've had to assume that germination of a plant is independent of a plant is independent. So you sometimes need to contextualize those 4 conditions we looked at. So germination of a plant is independent of others. And you might think, well, how would I know that? Because it's to do with this model. So you just relate it to the context. So basically what we mean by that is it's not like you don't have like a bad batch. We're not assuming that there's these quirky scenarios where if one does it, that makes the next one more likely. They're independent. For us to be using a binomial model, that would have to be the case. And we also say that the probability of germination is constant. So we sort of specify the conditions relating to those bullet points. And so there we go. We're going to state those assumptions there. Okay. Right, very good question. Would a good assumption be there can only be 2 outcomes? So yes, you are right, it would. I wouldn't personally state that one because it's the kind of more obvious one in that the question says the chance it will germinate is this, so it does or it doesn't, but you're not wrong. That is one of those bullet points contextualized as well. So yeah, there are 2 outcomes, it germinates or it doesn't. I would go with the ones that are less directly implied. But yeah, really good question. You're absolutely right. That would be valid. That is a point. And so that's exactly fitting it as we're saying. We'll give these 2 for now. These are typically the ones that aren't as obvious from the wording that we often like to state in the exams. But that was a really good question in the chat there. So let's have a little look at another scenario now. So on average, 25% of the packets of a certain kind of soup contain a voucher. Kim buys 1 packet of soup each week for 12 weeks. The number of vouchers she obtained is X. State 2 conditions needed for X to be modeled by the distribution by a binomial with 12 and 0.25. So what they're saying is the 12 weeks and the chance of it containing a packet of having a voucher in the packet is 25% of the time. So that's all there. The assumptions we would have made, so we're going to give 2 assumptions, 2 conditions, is that the probability, and again, it's the same sort of idea pretty much every time, probability of a packet containing a voucher is constant. So again, I wouldn't say it does or it doesn't contain a voucher because that's kind of implied more directly, but I'd go more for this sort of thing. So probability of packet containing a voucher is constant. So it's not more likely in a different shop or, you know, that sort of thing. It's constant. And every packet containing a voucher is independent of the others. So if it's on the shelf next to another one, that doesn't make it more likely or less likely. So event, I don't know what I'm writing here, every no, sorry, I did mean the event of, or the chance of a packet containing a voucher, this scenario, this event containing a voucher is independent of others. Does that make sense to everyone? Is independent. It's not being influenced or affected by what's going on around it. It's independent. It's its own separate scenario, not being affected by the fact that someone else just got a voucher. Does that make sense? So they would be the conditions that we would say, yes, so that's following a binomial distribution. If these things were in place, if this was true, if it was truly independent and a constant probability, then it actually is fitting this model. It's working really well. It is this distribution. The chance is consistent. I'm doing this many goes. It's not being influenced by other things, so I can calculate it. And these assumptions are really important for modeling mathematically. So let's look at one more question like this, and then we'll actually do some calculations, and I'll show you some maybe calculator shortcuts and techniques as well for doing binomial calculations. Here we go. Last one of these. Andrew plays 10 tennis matches. In each match, he either wins or loses. State in this context 2 conditions needed for a binomial distribution to arise. Now, again, I wouldn't say he either wins or loses. There's only 2 outcomes because they've told us that. That's not an assumption. They've actually said that explicitly. So that's great. That's one thing ticked off. But what we've had to, in this context, 2 conditions we would have had to have assumed is we would again, the probability of winning each match is constant. And this might feel very repetitive or quite straightforward, but probability of winning each match is constant. The reason that is important is because it's not assuming that if Andrew plays a game and he does well, the next game he's more confident, he's more likely. We're just saying it's just constant. It doesn't matter who he's playing, it's a constant chance. So probability of winning each match is constant for us to use this model. And then the other one would be that each result is independent. So it's not having a knock-on effect. Is independent. Yeah, yes, very good question here. Absolutely. I'm going to answer that now. That was really good question. So independent of others. Now, this is how we answer the question. Assuming these conditions, define a variable in this context. So for part B, I would say let X be the random variable. Oh no, sorry, let X be the number of matches Andrew wins. This is the thing we're trying to work out. This is the thing we're trying to assign probabilities to. So X be the number of matches Andrew wins. Andrew wins, and we would then say that X follows the binomial distribution with 10 matches and probability of success as P, because we haven't actually been told it. But if I get told it, I can sub that in. So that was really good. So we're not saying it's equally likely. If they said he's equally likely to win and lose, I would put P as 0.5, but they haven't told us it, so we just put P. So that was a really good question, and I like that so many of you have picked up on that, challenged it, questioned whether we should just make up a value. So it's, yeah, so in most contexts, you're going to be given that, or maybe have to work it out, but if you're not given it, that's as far as we can go. We know N, we don't actually know P yet. It might be later in the question they tell us. Really good, great questions and answers there. Well done, guys. So what we're going to do now is actually do some calculations, go a little bit further into this topic, and I'll show you some other ways of doing it on the calculator as well. So here's a good example, binomial distribution examples. At a bakery, there is a 10% chance of a loaf from a batch being undercooked. Calculate the probability of there being exactly 4 undercooked loaves from a batch of 12. This is a binomial question. This is very much exactly the thing we're looking at. So I'm going to say, let's let X, the random variable we're dealing with, be the number of undercooked loaves. So like in this scenario, a success is undercooking the loaf, because that's what we're dealing with. So let X be the number of undercooked loaves. So you wouldn't generally think, oh, I've successfully undercooked it, but that's the thing we're modeling. So that's what we're calling the variable. So the undercooked loaves is what X is. And we would know that X would follow a binomial distribution where N, the number I'm dealing with, is 12, and the chance that I undercook it is 0.1. 10% of the time is I'm going to successfully undercook it. So this is the model. Is everyone clear that that's the setup we're going with? So I want to find from this model the chance that 4 of them, specifically 4, are undercooked. So what I would do to find the probability that X is 4, I would do 12 choose 4 times 0.1 to the power of 4 times 1 minus 0.1 to the power of 12 minus 4. So basically, the number of ways it can happen times 4 successfully undercooked times together, and then the other 8 of being cooked properly, and that would be a probability of 90% of the time. So basically what I'm doing, oh, the squiggly thing basically means that the variable follows this distribution. So there's other distributions from the binomial. It's not just the binomial distribution that we have. So that letter denotes it's following that distribution. It could be following something called the normal distribution or different things that we'll see in statistics. But that squiggly thing means it follows that distribution. That's how you'd read it. Great question. So no worries. So what we've done here is we said 12 choose 4 is the number of ways of across 12 branches I can specifically restrict 4 outcomes and in turn restrict the other 8. So 4 undercooked and 8 properly cooked. So 12 choose 4. So on your calculator, you would do 12C4, 12 shift divide sign would get the C and 4. And that would tell you how many different ways of arranging those items with like undercooked, cooked, undercooked, cooked, how many different ways that could pan out over 12 like batches. Times the chance of undercooked times undercooked times undercooked times undercooked times all the rest of them being properly cooked. And so I'm going to do times 0.1 to the 4 times 90% of the time. And there's going to be 8 of them that are cooked properly. So there is another way on the calculator. I'll talk about that in a minute. But can everyone try this? Try this on your calculator. Whatever calculator you've got, we're going to do 12 shift and the divide sign, time 4, 12 choose 4, times 0.1 to the 4, times 0.8, sorry, times 0.9 to the power of 8. And what we would get is that will come out as 0.0213, and typically 4 decimal places for probability is kind of acceptable. So that's really good. Now, there is a way for those of you that have the class whiz calculator for A-level with the white back, there is a way that you can just type in the model and it will give you this answer. So if you have this and you'd like to follow, if you go menu setup and you go 7 for distribution and scroll down to number 4, which says binomial PD, and then you type option 1, list, what you could, option 2, variable. Let me do that again. Binomial PD, and then you go variable, and then you type X in as 4, N in as 12, and P in as 0.1, press equals. It straight away gives you that same answer we found. So this is the binomial PD you can use on here. In terms of the number of ways it can happen, that's absolutely fine. You don't need to get too caught up. So if you've tidied that up to 495 ways and then you've timed it out and found the final answer, that's great. We're not too concerned about how many different ways it can happen. We just care about the probability overall of coming out at the end of it with 4 undercooked and 8 properly cooked. And that's what that figure is there. That's the chance of it happening any of those 495 ways. Ultimately, it happens about 21% of the time. So under this model, where it's 90% going to be cooked properly, I've got 12 of them. The chance that 4 of them come out undercooked would happen 21.3% of the time. So that's what we've basically found. Is that clear to everyone? Does that sort of make sense? Do let me know if you've managed to do it on the class whiz as well, because it's very handy that you can use that setting to just type in X, N, and P, just work the probability straight out. So let me know if that's worked out okay for you. Cool. So I'm going to carry on and we'll do a few more questions like this. Yes, that sounds right. So if that was your answer for, so that was 12 choose 4, let me just check, is 495. Yeah, that's the number of ways, but that's not really what we're looking for. That's just part of the calculation. That's how many different ways that could happen. But then we work out the probability times the 495 different ways it could happen to say that ultimately the probability of coming out with 4 undercooked out of 12 is that answer. Yeah, so that was a really good question. So let's keep going. We'll look at another example here. So this one, it says let X, and we're going to say it's a, six-sided dice. So calculate the probability of throwing exactly 9 sixes from 40 throws of a fair die. So what I'm going to do is say, let's let X be the number of sixes thrown. Okay, and do feel free to work ahead and try and work this out. Then we would say that X follows the binomial distribution, with 40 as N and 1 in 6 as P, because if it's a fair die, then the chance is 1 in 6. Should really say fair six-sided die, but we're going to just assume that for now. So what we do is we're looking for the probability of exactly 9 out of that 40. So the way we'd work it out is 40 choose 9 times the chance of successfully throwing a 6 9 times not throwing a 6 the remaining 31 times. And if you guys want to calculate that for me, that would be great. Absolutely right. Well done to those that have done it. 0.0953. So under this distribution, the chance that I come out with exactly 9 sixes is almost 10% of the time under this distribution. So rather than doing a 40 branch tree diagram, I've worked out the probability and all the different ways accounted for and so on. So it's a really powerful method. Now, again, you could have used the class viz and just typed in X as 9, N as 40, P as 1/6, and it would have given you that value straight away. But it's hopefully not too hard to work out from just the sort of formulaic approach. So hopefully that's clear. Do ask if you're unsure though. What I'm going to do, I'll just do a little checkpoint and then we'll do a couple of exam questions. So let me know how you're finding that. Straightforward, okay, or a little bit confused. But do let me know because this hopefully can be consolidated and we can look at some more sort of scenarios here. So let me know how you found that. So just a 1, 2, or a 3. Give me an idea of how confident you're feeling with it. And then what we'll do is we'll move on to a few more exam questions and sort of pull them apart and work out what's going on. Lovely. So do let me know in the chat. It's great to see some people have answered that already. Thanks very much. We're going to keep going, but do feel free to still share how you found it and do ask at any point. So this one already now looks suddenly really wordy. An express coach travels daily between Middlesbrough and London. When the coach calls at Thirsk, it is possible to purchase a seat on the coach, providing seats are available. The probability that the coach calls at Thirsk with at least 1 seat available on any day is 0.4 and is independent of that on any other day. Calculate the probability that during a 28-day period, the coach calls at Thirsk with at least 1 seat available on exactly 7 days. So it's like, wow, that's very wordy. Welcome if you just joined. Feel free to ask any questions and share answers as we go. So what we've got is to just do exactly like we've been doing it as a binomial model. We're going to let X be the number of days the coach calls with an available seat. Coach calls with an available seat, with available seats. Right, and we're going to say using the call notation, not sets, seats. X follows the binomial distribution with N as 28, because it's 28 days, and the probability of successfully having a seat available is 40% of the time, 0.4. So then what we do is we want to find the probability that X is exactly 7 out of that 28-day period. So that will be 28 choose 7 times 0.4 to the power of 7 times 0.6, the chance it doesn't have a seat, to the remaining 21 days. And that should come out as 0.0426. Okay. Then it says, just for 1 mark, indicate why a single binomial model would not be appropriate for the number of calls per month of a coach at Thirsk. What do you guys reckon for that? What would we comment for the 1 mark there? Why couldn't I just use this model for every month? What is the problem? Why doesn't this fit the binomial scenario? Why couldn't I go, I've just worked it out for 28 days, so I could just always use that? What is the problem with using this binomial model to be representative of all months per month? Let me know in the chat. Very good. Thanks for those sharing answers. The number of days in each month, and therefore each trial, is not fixed. And so that's a problem. That breaks the model, that breaks what we're doing. So it needs to be the fixed number. And because not all months are just 28 days, it's not actually a good model to use always for all the different months, because some have 30, some have 31. So it's the wrong number and it changes. So even if we pick 30, that would be no good. It has to be something where the value for n is the same, and it's not for months. It's not for the days in a month. So that doesn't work. Well done. So then we'll just quickly look at this one. So given that P equals 3/4, actually, yeah, let's do this one quickly. So P equals 3/4, find the probability of X equals 5. So you guys can work that out for me. And let's check we agree. So you can use your calculator, but we're doing 11 choose 5 times the probability of success to the power of 5 times the probability of it not happening to the power of 11 minus 5. So 6. And let me know what you get. So let me know if you've done it. Do feel free to share your answer in the chat. And then lovely, well done. Excellent to those that have done this. So 0.0268. And then for the second part, given that the chance of X being 0 under this distribution is 5% of the time, then what we know is 1 minus P, the chance of failure, must have happened 11 times. So for probability of X to be 0, to have no successes, you know it's that scenario where it's just failed every time. So it would be the probability of failure, 1 minus P to the power of 11 times like the other scenario, no times. So literally just 1 minus P to the 11 must equal 0.05. So then what we can do is we can 11th root both sides, add P across and take it off of 1. So P is equal to 1 minus the 11th root of 0.05, and that will be equal to 0.2384. Okay. So this one was a little bit weirder. This was like a bit different, this one, because the chance of it happening no times means that it's failed 11 times. So the chance of 1 minus P to the power of 11 must equal 0.05, and then we just rearrange it and find P. So that was a little bit of a different style question, that one. Right, what I'm going to do, I'm just going to skip this next slide and go recap what we've done. So we've looked at the binomial expansions that you might have seen in pure maths, and we've gone on to look at what a binomial distribution is within the realms of statistics and how it comes up in the stats side of the course. And using the idea of combinations and factorials to find that. And then we've also calculated probabilities from a binomial distribution. We've also looked at the specific conditions of a binomial, because that is a really common question as well, and quite nice if it comes up. So that was really good. Brilliant questions and answers as we've gone through it. What I did also want to talk about is I'm going to quickly stop sharing that and just talk to you a little bit about some of the stuff we have in place for the A-level and for your revision. So if I just share the Snap Revise website. So for those that haven't seen this before, I did mention the discount code earlier for a 3-week trial of web classes. If you go over to the website and you go to the tutoring services, so for example, A-level maths, what we do is we have weekly web classes. So 4 a week, 2 for year 12, 2 for year 13, typically. Web classes on all the topics covered in all the A-level courses. So they run every week. Our classes, much like we've done here, fully comprehensively covering the whole A-level. And I also run drop-ins as well. So the drop-ins are for you to ask specific questions. Maybe it's a question you're struggling with from your homework. You might have an exam coming up and you just want some one-to-one sort of support guided on what you're doing. The group drop-in sessions, you can send questions in. You can ask me directly in those sessions. But we have the web classes and the drop-ins all on the site. And there's kind of a backlog, a catalogue of web classes you can watch as well on any topic you want. So there's loads there, as well as all the resources for kind of the diagnostic quizzes, the revision resources that are you can download and are really clear and easy to follow. So do check that out. And obviously there's a week free trial that you can sign up to and have a little look at. And every topic's covered. So the brilliant thing about the Snap Revise platform is it's tailored to the new A-level. So all the out-of-date resources and past papers that aren't geared up in the right way, this is spot on with everything that's happening with exams now and the course and the syllabus since it's been restructured. So it's a really good resource to look at that's bang up to date. In terms of the resources we've got, another thing that I did want to show you is we also have the flashcards that fully cover all the new courses. And yeah, they can be ordered online, but they cover questions and answers for every sort of type of kind of topic that can come up within the A-level, so you can kind of quickly test yourself as well. But there's loads of these really clear and kind of easy to follow resources on the site as well. So lots of kind of revision materials on there, but these flashcards are really nice to kind of test yourself quickly and have as preparation for exams. So it might be something you're interested in as well. But certainly the service for the web classes and the drop-ins, if you're interested and you found this useful, please do put the code in and try that out for a week, and you'll be able to see the other web classes we've run on all the different topics. So it's not just obviously for statistics, but the mechanics and the pure side of the course as well. And check out some of the other resources available on the platform, because as I said, they are geared up to the new A-levels and the different boards. So they're very specific and kind of focused, not only exam focused, but the content is really clear and easy to follow. And I'm sure, as you're aware, the A-level content is quite tricky and needs to be broken down very rigorously and concisely. And that is certainly done throughout all of the resources seamlessly. So do check that out. I'm going to just stop sharing that for a second and I'll reshare the PowerPoint we were on. So hopefully that's visible again. But yeah, just as a little reminder, the code at the checkout, if you are interested in trying the platform out for a week, is here. If you want to take that code down and sign up for a free trial and have a little look at the resources that are available to you on there. This is a really good opportunity and time to do that. Obviously, being in the summer, I know you're probably enjoying a bit of a break from school, but just to kind of, in a sort of passive way towards getting in gear for next year, it might be nice to see what resources are available. And obviously, it's been great that so many of you have joined this session today. answered and asked questions really well throughout. But if you're looking for resources and gearing up for year 12 or 13, this might be a good time to sort of try stuff out and see if it's for you, if it works well. If you have any questions, let me know. Thanks again to everyone for joining and taking part so well today. I hope everyone's having a really good summer and you're all keeping well. I'm going to stop sharing that now. We do obviously have other YouTube sessions coming up. So if you'd like to set a reminder for those, it would be great to see you at some of these future ones that we're running on YouTube as well. And I hope that's been useful. Very well done again to everyone. And thanks very much for taking part so well. So there's the discount code. I think it's in the chat as well there if you want to have a little look. And hopefully we'll see you at some sessions in the future. Really well done. I'm going to stop sharing that there and just say thank you again. And yeah, enjoy the rest of your summer and keep well. Thanks, guys. Take care. And yeah, hopefully see you at a future session. Well done. No worries. Thanks, guys.